Hi, my name is Paul Park, and for our project, we'll explain the early Earth and implications for the evolution of life. In our lectures for Bio 1520, we learned about a few things that happened in the early Earth throughout the geologic timescale. Take a few seconds to see if you can remember some, if not all, of the events that occurred in the Archean and Proterozoic eons. We'll see how you did now. In the Archean eon, we have the origin of life, first evidence of photosynthetic cells, and first evidence of oxygenic photosynthesis. In the Proterozoic eon, we have oxygen in the atmosphere and ocean, and the emergence of eukaryotes. Another important event that I want you to be aware of is the Cambrian explosion, because we're going to ask the following question. What were the atmospheric, geological, and solar conditions like in the early Earth, and how did they affect the evolution of life, leading to the Cambrian explosion? Two major topics that we'll cover in this presentation are the faint young sun paradox and the Snowball Earth hypothesis. Although they're still relatively new concepts, they can help us understand the conditions of early Earth and how they led to the diversification of life. During the times of early Earth, the sun was much dimmer. It produced about 70% of the energy output of today's sun. With smaller energy output from the sun, the planet should have been frozen for much of the Archean era. However, Earth was ice-free for the most of the time. The evidence for this comes from the presence of sedimentary rocks in the Archean strata. This contradiction serves as a basis for the paradox. In this slide, we have a graph of solar luminosity with respect to time, which clearly shows the increase in solar energy output with time. There are a number of possible explanations for the paradox. One of them points to the enhanced concentrations of reduced greenhouse gases. Increasing the concentration of reduced greenhouse gases, which include carbonyl sulfide, carbon dioxide, methane, and ethane, allow for a higher temperature of the planet. This mechanism worked in the same way as the global warming phenomenon we see today. As we can see from the figure on the slide, there were high levels of CO2 and methane around the Archean eon, which starts around 3.8 billion years ago and ends around 2.5 billion years ago. The temperatures, which are given in Celsius, also remains high throughout the Archean eon to prevent freezing over of Earth. Other possible explanations point to lower albedo and faster rotation of Earth's axis. Albedo refers to the reflecting power of a surface and includes factors such as cloud coverage and terrain type. With lower albedo, much of the heat and energy from sunlight will be captured by the surface, raising the temperature of a region. As a real-world example, the albedo of the desert is much lower than the albedo of the snowy plains. On the other hand, faster rotation of Earth's axis can prevent freezing over by reducing the duration of cold nights and therefore preventing the temperatures from getting too low. What are the evolutionary implications for the faint young sun paradox? Because the early Earth did not freeze up and liquid water was widely available, it was possible for life to start on Earth. Because of the lower energy output of the sun, photosynthesis was not as effective as it is today, and the development of photosynthesis might have been delayed. And when it finally did develop in the Archean, its limitations placed a constraint on early life forms. With high concentrations of CO2 and lower concentrations of oxygen, photosynthesis was anaerobic for much of the Archean, and oxygenic photosynthesis was not developed until much later. Now we'll talk about Snowball Earth. Snowball Earth refers to periods in which Earth's surface became entirely or at least nearly frozen. There have been many snowball episodes throughout the Proterozoic eon. The average ocean temperature got as low as 275 kelvins or 2 degrees Celsius. As was the case with the faint young sun paradox, there are explanations as to why Snowball Earth took place. First of these is the breakup of low-latitude supercontinents. At certain angles between the Earth's axes of rotation and orbit around the Sun, mean annual temperatures were lower around the equator than at the poles, thereby making glaciation more probable at lower latitudes. The figure on the slide shows you the change in the global mean surface temperature with time flowing from bottom to top. As the map on the right shows, a lot of the continents were in lower latitudes, suggesting that their placements contributed to a significant drop in temperature. Another explanation for Snowball Earth points to collapse of methane atmosphere. According to Pavlov, because atmosphere methane is not equilibrated with the ocean like CO2, breakdown of the methane supply could trigger Snowball Earth. This is highly speculative, but if you take a look back at figure 2, we can see that the methane level drops considerably around 2.5 billion years ago. It should be noted that one of the major snowball events occurred around this point in time. It is possible that the drastic decrease in methane level may have caused Snowball Earth. Another explanation for Snowball Earth looks to reduction of volcanic activity. Volcanic activity is one of the major factors that affect atmospheric CO2 level. As the figure in the slide shows, ice level increases as the CO2 level decreases. It may be possible that the reduction in volcanic activity may have caused the CO2 level to drop, which in turn lowered the mean temperature of the Earth, causing a snowball event. Snowball Earth has some important evolutionary implication. Even though it may seem that life on Snowball Earth would have been near impossible, extant clades of prokaryotes and eukaryotes are known from before Snowball Earth thanks to fossils, so life on Snowball Earth was possible. But because of the climate shocks caused by extreme temperature, various refugia, which were teeming with nutrients, thanks to hydrothermal activity and limited organic productivity, were created throughout Earth. This gave room for allopatric speciation, allowing diversification of life possible. And consistent with Figure 2, greater levels of oxygen would be available thanks to the newly enhanced organic productivity and organic matter in the various refugia, making life possible for more complex and bigger organisms. The most important implication for Snowball Earth, however, is that the possibilities of diversification of life leads nicely to the Cambrian explosion. The faint young sun paradox and the Snowball Earth hypothesis can help explain the origin of life and the early evolution of life, as well as how the Cambrian explosion came about. Perhaps without the diversification of life made possible by these two phenomena, we would not be able to see the wide variety of organisms that exist today. Thank you for watching this video, and I will now end the presentation with a works cited page.